Hey guys, this is Mr. Yo, and today what we're going to talk about is exo and endothermic reaction, following with another lesson called bond energy. So please make sure if you guys are stuck, make sure you rewind and rewatch that section of the lesson. And without further ado, let us begin. So first thing first is the introduction of what a potential energy diagram is all about. Why are we learning about these stuff? Number one, it's something related with stored energy, the energy that is stored within, especially in a bond. Now, always remember, this was mentioned previously with the balancing equation notes, is that the beginning is always called the reactant. This is called the beginning stage. And then if there's a beginning stage, there's always going to be an ending stage or the outcome. Now, however you guys want to phrase this, that is all up to you. Last time I talked about reactant being beginning, an English term, and product being ending, or in math terminology, reactant being input and products being output. And something we also are going to go over is called the heat up reaction, or the delta H. Which I will mention within this lesson. Endothermic and exothermic. One being positive while other being negative. Okay, so this is kind of like a summary of what we're going to learn today. So make sure at least you guys have a small grasp of this lesson. Now, this may be something you have learned from biology class or from middle school science. So this lesson might be a bit easier than you guys expect. So let's actually talk about what the potential energy diagram actually includes. So first thing first, we originally mentioned about the word reactant, which is located in the beginning stage. Okay. Or we call it the starting point. And then we have something called the product stage. Now the product, well, if there's a starting point, there's an ending point. Now, when you guys drink an energy drink, what happens to you whenever you drink some caffeinated drink like coffee or let's say Red Bull or Monster or whatever energy drink you guys nowadays drink? Well, after you guys drink those things, you get all these energy being starting up. So your body is starting up like an engine after drinking those things. And that is something called an activation energy. Activation energy. That's what we call it in this case. Or we sometimes call it the E and A as a subscript. So it's the energy needed to start the reaction. So that is called the activated energy. Now, later on, I'm going to explain to you how to find these values, so bear with me on that part. Now, after you drink the energy drink or coffee, you get to a certain point where it's your climax. It's the place where you get super genius or super full with energy for playing sports or doing your work, or filled with a lot of concentration. That is something called the activated complex. Usually what I call it is the peak. Just like that. Now, one last thing is the part where we have the distance between the product and the reactant. We call this part as the heat of reaction or the part that I mentioned about from the summary is delta H. So this is the part where we can actually figure out, do we have enough heat being produced or do we not? Now, in order to calculate this, I usually do product minus reactant. So make sure you guys have all of these parts within the chart itself. It will help you guys understand how to solve some problems, which is basically understanding how to interpret the graph that you see right now. So make sure that you guys have that in mind before we move on to the next small details about endothermic and exothermic reaction. Okay, so let's talk about what endothermic is. Endo, if you guys don't remember, I might have to use there you go. Endo basically means enter, or sometimes you call it absorb heat. So endothermic reaction is when the activation energy is large for endothermic reaction. Just like as you can see from this peak all the way to this reactant, it's pretty big. The reactant is lower than the product. So as you guys can see, the product is much higher than the reactant. Now, what does that mean if that's the case? Well, that means that the delta H, or the heat of reaction, will become positive if you calculate it. Okay. So make sure you guys have that down. There is some typo that's written on here, which should have been an arrow sign. So basically what it means is in a chemical reaction, heat is going to be within the reactant side. Just giving you guys a heads up. So always remember this part. Heat will be on the reactant side. Okay. So yeah. So as you guys can see, the graph on the left side is basically describing into words on the right side. So that's why in a normal lesson, I wouldn't actually read this whole thing because it's pretty much the same thing mentioned on the left and the right. But just if you understand the graph itself, like I said, then the words on the right side would be a piece of cake. So the key thing are these markings that I mentioned. Okay, the activation energy and the heat of reaction will tell you the difference between endothermic and the exothermic reaction, which we'll mention in the next slide. Here we go. So now let's talk about exothermic. Exo means basically exiting, or sometimes we call it release or releasing heat. So just like the words I mentioned on the right side, pretty much same thing on the left of the graph. So activation energy is small for the exothermic reaction. So as you guys can see, from the peak to the reactant, it's way smaller than what we have seen on the endothermic reaction. Now, the difference with this one also is that the heat of reaction will become negative, because if the product is small number minus large number will give you a negative value. Okay? And one small thing I want to fix again is that there should be an arrow sign right here. And also remember that heat, since it's being released, it's going to be in the product side. And there you have it. So that's the difference between endo and exothermic reaction. Now, how in the world am I going to interpret this or have this included with what we have learned previously about solid, liquid, gas? Well, if I move on to the next slide, exothermic is releasing or exiting. Endo means entering. So if that doesn't make any sense, think about this. If we have an ice cube, and if the ice cube contains a lot of heat inside its body, then what happens? Well, it's going to melt. If it melts, it becomes liquid, or let's say water. And obviously from water, it's going to become gas. Vice versa, if we don't have much heat, then it's going to go from gas to liquid and liquid to solid. So think about endothermic as having heat and exothermic as in, it's pretty much the same definition as I presented before. Releasing heat. Releasing heat. That's pretty much the difference. So there's nothing much to explain about this except, like I said, understand what the graph is saying. So now that you know the basics of this knowledge, let's try to solve some questions. So the first question says, what is the heat of reactant? Well, if you guys think about it, reactant, we know, is located from the beginning. So reactant right now we have is 100. So what we're going to put is 100, but don't forget the unit, kilojoules. 100 kilojoules. Okay. Then how about the product then? What is our product going to be? Well, the product right now is from where the product is all the way down to the bottom, because if you guys don't remember, product is basically just a product. There's nothing we subtract or anything. So this peak right now is 200 kilojoules. Okay, so we know that part. Now the other question is asking is, what is the activated complex? So sometimes the questions will be presented about like really hefty with words. But the key words that you just have to remember are those words that we mentioned previously. So activated complex, as you guys can see, is the peak. Now if we mention about the peak, let's see what that value is. So it's around the halfway point. So why don't we mention it as 325 kilojoules. Oops. I meant for that answer, since I don't have room. So activated complex is 325. Now let's try the other ones then. So if you think about it right now, the next question says, what is the activation energy? Now, activation energy is basically the energy that we get from drinking energy drinks and coffee. So that's basically from the peak all the way to the reactant. So how in the world are we going to calculate that? Pretty simple. All we're going to do is the peak, which was 325, minus our reactant, which is 100. And that gives us 225 kilojoules. Right there. So I'm just going to write down that word again. So peak minus reactant gives us activation energy. Now, last but not least, let's talk about the heat of reaction, or delta H. Well, always remember, heat of reaction is this area right here, which contains from the product to the reactant. Now, always do product minus reactant. Now, if we calculate this, we get the product was 200 minus 100, which will give us 100 kilojoules. Okay. Now, also at the same time, what type of reaction will this be if we know that part? Well, remember we said that the activation energy will look a bit larger, and also the heat of reaction is a positive value, which we have it right here. It will be an endothermic reaction. And that's how we determine this graph. If you guys have any questions, feel free to rewind and watch the previous sections of the slides. If not, let's move on to some more details. So that's basically the graph that you have to understand when you're finding the values for each parts. Now let's talk about catalyst. What is a catalyst? So this is something that you guys heard from biology and maybe life science and some other science classes in middle school. Catalyst, if you guys don't remember, the word that you guys have heard is called speeds up the reaction. Okay? It speeds up the reaction. Now, if you don't remember what it looks like, it's basically, I might choose another color. It's this section right here. The dotted line. This is showing that the peak gets lowered down. Or sometimes, I don't know if you guys have heard of this from your teachers, is that when a rabbit, okay, I am not a good drawer, but let's say we have a bunny, okay, and the bunny wants to jump over the hill. As you can see, originally it was too high, but with the catalyst, the bunny has to jump only a little bit compared to the previous one. So catalyst will help us actually jump over faster than the previous time or previous section. So the main key thing about chemistry, though, in biology we say speed up reaction. In chemistry, the key word to this is lower activation energy. Very important. It lowers the activation energy. Or sometimes your teacher might say it lowers activation energy or lowers activated complex, which is the peak. Either one will work out, depending on what the question is referring to. So please make sure that you guys have this marked or written somewhere, because it is very important that you know what a catalyst does in a reaction. Okay, so that's pretty much the first part of the lesson for potential energy diagram or endo and exothermic reaction. So feel free to rewind and rewatch that materials if you guys are stuck. Now, let us move on to our next lesson called the bond energy. Now, bond energy, it may sound a bit, it sounds easy. I mean, the title isn't that bad, but bond energy contains two things. Number one, Lewis structure. So if you don't remember how to draw a Lewis structure, I would highly recommend you guys to go over your materials. Number two is to plug in value and add or subtract. So that's the step number 2 section, which basically that's pretty much it if you follow those steps chronologically. So let's talk about this. So bond energy, it tells you the amount of energy requires to break a bond. Because if you guys remember from single replacement and double replacement, when we mentioned about, and decomposition too, when we mentioned about relationships, they break apart or they cheat. How do they do that? Well, that's what a bond energy will help you understand. It helps you understand how to break those bonds between the elements or between relationships. But anyways, so a positive value means the bond breaking is an endothermic reaction, just like delta H or triangle H that we talked about from potential energy diagram. So just like it says, the triangle H. Now, if you don't know what RxN is, which is totally fine, it's basically reaction, written in short. Enthalpy change or change in energy. The unit is kilojoules per mole, and all bonds in the reactants are broken to form new bonds in the products. That's pretty much all the definition, but make sure that you keep this in mind, though, right here. This formula will save your life in this lesson. So make sure you keep that in mind. Okay? So let's try to solve some questions. So an example question. If we have H2 plus F2 creates 2HF. Now, this lesson is not that hard. Okay, it's not hard because all you got to do are the followings. If you look at H2 actually, this creates H and H, but remember that each one of them has one valence electron. We're just going to connect them just like that. Now, I'm just going to make sure that the plus sign follows through. So I'm just going to put a plus sign following with, let's say, the F2. Same process, but here's the thing. You don't actually have to be that technical. What I meant by that is if I were to draw F2, a lot of you guys will definitely draw those 7 valence electrons, including in each of the F, which is totally fine, but I think it's kind of pointless in this lesson. Here's why. All we care is how many bonds are created in each element. So example, F has only one bond. So all I care about is the line in between like this. And I'll show you why. But after we set up the Lewis structure. And then for the next one, not a good way to memorize it like this, but I like to keep the arrow sign as a minus sign, okay? Because if you remember, it's basically the energy bond breaking minus the energy bond formed. Reactant minus product. So make sure that you guys keep that in mind from the equation on the previous slide. Okay, now if I were to draw the next one, we have HF. HF, well, if I draw the Lewis structure, it looks like this. But like I said, we don't care much about the lone pairs. So I'm just going to put HF. Now there is a coefficient too. So I'm just going to put 2 times HF. And all I'm going to do now is I am going to plug in the values based on the table that you guys see right here. That's the table and that's the value that it will be given when you're taking the test or quiz. We don't expect you to memorize those values because there's a bunch and it's a lot. Okay, so let's try to plug it in. HF, we have 436. Plus, we have F-F, which is 155. Minus, we have 567 for HF, so we do 2 times 567. Now, if you plug it in, the value you'll get is negative 543 kilojoules per mole. That is the value you will get after the calculation. So make sure that you guys check your calculation. And the most important thing is check your Lewis structure. If you draw it incorrectly, then plugging in will be hopeless. Okay? And also, since it's a negative value, this would be an exothermic reaction. Okay? Now, we're going to have two more example questions. So if you guys want to try it out on your own, feel free to pause the video and just go on with it. Okay? So I'll let you guys, give you guys more time to work on this. Okay? So let's go over this lesson. So right now we have a following drawing. So I'm going to kind of skim through because I'm going to assume that you guys understand how to draw this. So we got H with H plus Cl with Cl minus 2 times H that. Okay. Now I'm just going to place a parentheses to keep in place that one side is a reactant while the other side is the product. And all I'm going to do is I'm going to plug in the values. Now, it's totally fine if you don't write this delta H reactant. That's all up to you. But just make sure that you plug in the numbers right. And get the correct answer. And there you have it. That doesn't look good. Let me redraw the box. There you go. Okay. Now, if you guys are confused where I got those values, well, I got it from here. This is 1. This is 2. And this is 3. There you go. Okay. All right. Try this question as well. And if you guys have any questions, well, feel free to look at the answer after you finish the question. All right. So this one's a little bit tricky because here's the thing. Well, first of all, I'm going to underline or I'm going to place the ones, box the ones that you need, the values. We have one right here. We have another one right here. Okay. And then we have another one right here. And then we also have another one right here. Now, how is this going to be drawn if you have a tetrahedral or CH4 or CH3Cl? That one's a little bit tough, but it's actually not. Let me show you how it's done. This CH4, if I were to redraw this, it will look something like this. Now here's the part. How are we going to write this down? I know there's only one carbon, but all we care about is what is attached to it. So for CH, we got 1, 2, oops, 2, why aren't you working? 2, 3, and 4. So how we're going to write this down is 4 times C-H, because there's CH's and there's 4 of those. And then for Cl, we know that it's Cl-Cl minus. For the CH3, okay, this one right here, CH3, so I'm going to make sure I draw those out. And then we have Cl. Same concept. I want a brighter color. There's CCl, and there is CH, CH, and CH. So right now we have 3 CHs following with a CCl. Plus, we got H and Cl together. And that's how we draw, or how we write down, after we draw the full Lewis structure and kind of getting the grasp it along the way. Okay? And last but not least, let's plug in those values and find out what our answer is. So we got 4 times 413 plus, we have 242. Let me put a bracket. Minus 3 times 413 plus 328 plus 432 of 1. And that will give us our final answer, which will be negative 104 kilojoules per mole. And there you have it. That's your answer for this question. So please make sure you review the previous lessons in order to help you understand how to do the bond energy, such as the Lewis structure. And yeah, and that's pretty much it. So review the notes. If you guys have any questions, feel free to ask. And other than that, I hope you have a wonderful day.